Thank you very much. So good afternoon, everyone. First, I would like to thank the organizers, the chair also of the session for having me here. And it's actually a great pleasure to be here to tell you a little bit about some of our recent work at the interface between the field of meta-optics and optomechanics. So I have some kind of a mission today that is trying to convince this community that is very good at engineering meta-surfaces that their knowledge could be very beneficial, basically, to the field of optomechanics. Just because I don't want to rush through that at the very end, I would like to thank my team. So this is a picture taken in the Engadin in Switzerland during one of our outings. And so the people that have been contributing to the results I'm going to present today are basically Bruno, Pedro, the two PhD students, Bin and Adil, two postdocs. And I would like also to particularly thank Nadine Meyer, who is a senior researcher in my group, who has been really helping me a lot in coordinating these activities in the team. So we're going to be talking about optomechanics. So I'm sure like many people in the room are actually already familiar with this concept, but this is basically the field that studies systems where the electromagnetic field is coupled, is intertwined with the electromagnetical field. So there is a typical model system that is shown here, where you have a fibrillar cavity with one of the mirrors actually on a spring. And the idea here is that the intracavity field, because of radiation pressure on the surface of the mirrors, are going to be optomechanically coupled, basically, to the movement of this mirror. So during decades, this field has been fascinating researchers with different motivations, one being like pushing, let's say, quantum physics with large objects. But there's also like a little bit more applied motivation, one being high precision, the development of high precision sensors, or also developing transducers and actuators, as actually in part also discussed by Nikolai Geludev this morning, talking about metrology. So there is a full jungle of optomechanical system in the literature, and I would like just to show things that are probably familiar to this community. So pioneering work from the group of Tobias Kippenberg at the PFL, some engineered membranes, these photonic/phononic crystals, and more recently, a system proposed by the group of Nikolai Geludev based on these plasmonic optomechanical metasurfaces. So today what I would like to do is actually focus on one specific aspect. So using meta-optics, and what I mean here is using in particular some dielectric system and playing with the engineering of the mirror resonances in these structures. And I must, before talking about the work, actually acknowledge these three works. There's kind of a selection of works that actually strongly inspired us. So the first one is actually back in 2015. This is actually from the Geludev's group. And this is, to my knowledge, the first time that it was shown that an optomechanical actuation could be used to change, let's say, the transmission through a metasurface. Another very interesting work, this is from the Atwater's group in Caltech, and there's a more recent paper showing an experimental demonstration of that, is actually the possibility to engineer a suspended membrane with some meta-gratings in order to create self-stabilization when they are pushed away with the light. And finally, this work that is from the Scholz group in Chalmers, that is very interesting work, having this meta-vehicle decorated with some meta-gratings, and to use light actually to steer them on the surface in a very controllable way. So our first let's say, work, our first project in this field of optomechanical metasurfaces was actually a very simple motivation. We wanted to achieve a reconfigurable, ultra-thin optomechanical metalens. And so the idea is quite simple. What you see here is actually a silicon membrane that has been patterned. And you can see here some nano beams. And along these beams, you have an arrangement of meta-atoms that have been designed to focus light of the probe beam, so this red color, and so obtain with that a meta lens. And then I use a second color, that is the pump beam, that is the green one. And the idea is that this pump beam is actuating via optical forces on the structure, deform the structure, and therefore you can, with that, change the focal distance. So if you look at the details of the structure, so this is how each meta-atoms look like. So you have a silicon cylinder. The thickness here is 200 nanometers. It has a radius r, and this is connected to the beam via this short connector. And if I take, let's say, an array of identical structures like that, and I calculate the transmittance, what will happen is that I'm going to observe two regions. A region in blue here that is more related to the electric and magnetic dipole supported by the disk, so something that we know very well. And the second one is actually an hybrid mode, that is a mode hybrid between the beam and the cylinder. So you see what we're going to do. What we're going to do is that we're going to use these two modes in order to engineer the phase for the light that is going through the system, and this is what will enable us to create a library of meta-atoms in order to create the lens. And we're going to use this other resonance, the hybrid resonance, at 1550 in order to actuate on the system. When I'm going to shine light, exert a force on the structure will bend, and I will create an additional phase shift. And this is what will enable me to change the focal distance. So this is how it looks in practice. This is the structure that was fabricated by Adil Afridi. These are the features. So here you don't see much. If I zoom a little bit more, what you see, these beautiful meta-atoms that are connected to the nanobeam. So this is prior to the etching, but basically, normally these things would be suspended. So the experiment we did is very simple. We're going to use this two-color scheme, so the probe and the pump, and we're going to reconstruct at zero pump the focal spot, let's say, of the meta lens. And then we're going to, so these are experimental data, and so when we switch on the pump, what we see is that we change the focal distance in a very clear way. In that case, for this intensity, we have a change of 20 micron. And so, of course, we can do that in a very continuous way. And so what you see here is that tunability of the focal distance as a function of the intensity that is used for the pump beam. So this is the first story and the first project that brought us basically in these fields of optomechanical metasurface. And I would like to show what is next. So what we wanted to do is that not only we wanted to use meta-optics to create some actuation, some reconfigurability, we wanted to show that we can exploit the full toolbox of meta-optics in order to engineer metasurfaces that would experience optical forces that would be actually very difficult to obtain with a natural material. In particular, we're interested in engineering the sign of optical forces. So I don't know how familiar you are with optical forces, but basically two things to remember. If I shine light that is unfocused on the surface, what will happen is that I will exert pressure, radiation pressure. And the second thing is that if I have a gradient of intensity, solid matter will be attracted by the intensity maximum, okay? And I want to show you that we can use meta-optics in order to overcome, actually, these very general rules of optical manipulation. So just imagine we have this system. This is an array, again, of meta-atoms, but the system is slightly different. This is a grid this time. You have the cylinders. The thickness is a little bit larger, 350 nanometers. And we're going to have two parameters. We're going to have the radius, and we're going to have the pitch of this array. And what I show on the right is what Adil calculated. That is basically the polarizability of the first 4 multipoles that are supported by this array as a function of the radius of the cylinders for a fixed wavelength and a fixed pitch of the system. And what you see here, if you look at one any of the curves, you're going to see that, for instance, there are regions where you're going to have a positive value for the polarizability, and there are regions where you're going to have negative values. So now, let's be a little bit more concrete and imagine an experiment where you're going to have two waves, forming a standing wave pattern. So two 1550 lasers. And so we're going to calculate the force experienced by the metasurface I've shown before when located at the inflection point of a fringe of the intensity pattern. And now we're going to calculate the force along the z direction, and we're going to observe that indeed we're going to have, as a function again of the radius of the meta-atoms, regions where the force is going to be positive and regions where the force is going to be negative. Interestingly, it's possible to show that in first approximation, despite the fact that I'm very far from being in the dipolar regime, we can actually show that the force is, in first approximation, proportional to the gradient of the intensity times an effective polarizability. And if you look at the expression of this effective polarizability, we did that empirically originally to find the best agreement. And this is what you see here with plus and minus. And so we observe that the region of negative force correspond to regions of negative polarizability for this effective polarizability that account for all the multiples. So this is the structure that was fabricated, again, by Adil Afridi. And so we see here the central part of this silicon membrane that is patterned with this array of meta-atoms, and the system is softly clamped to the rest of the membrane. This is a zoom where you can better see the details with the different cylinders and the connectors between them. So now we would like to show that it's possible to observe the change of sign in the force that is experienced by this, let's say, solid state system. This is not an atom. There is a kind of analogy you can imagine with what people are doing with cold atoms. So how we're going to measure the force, this is what I'm showing here. So you have a kind of a pump and probe system. So just imagine we take a 1550 beam. We're going to split it in two beams, a pump and a probe. So first the pump. The pump going to form the standing wave pattern I was showing in the simulation. And what we're going to do is that we're going to modulate this with an AOM at the fundamental mechanical mode of the system, that is around 90 kilohertz. And then we're going to use the other part of the beam that's going to be cross-polarized, going to interact with the membrane, and going to be reflected, and we're going to send that to a lock-in amplifier in order to extract amplitude and phase. So why phase? Because we need this information in order to extract the sign of the force. I want to convince you with a very simple animation, nothing very rigorous. But so basically, this would be two situations of a positive force upon driving and a negative force. In the case of the positive force, so the displacement of the membrane would be in phase with the modulation. It would be out of phase, of course, in the case of a negative force. So before doing the experiment, Adil computed this entire, let's say, this graph where we explore the whole parameter space. So this is the pitch, this is the radius, and basically what is selecting here is two structures, one that is expecting to give a positive response, the other one that is expected to show a negative response. And these are the parameters, corresponding parameters. So this is the amplitude of the mechanical resonance, again, centered around 90 kilohertz. They're slightly different for the two structures because, in fact, they have slightly different mechanical properties, so this is kind of expected. But then what is more interesting, of course, is the phase. And what you see here is actually first the positive case, let's say. So, of course, this is modulo 2 pi to connect to your textbook on a driven oscillator. And so this is zero phase across the resonance that become a minus pi, so modulo 2 pi. This is the typical pi phase jump across a resonance. And of course, and not of course, but actually what we were very happy to see is the second situation. So for the negative case, where you see that we actually have a pi phase shift first, and we come to 0 phase shift. So this thing is quite robust. So Adil, very courageous, has been like fabricating many structures, covering like different regions of this simulation I was showing before. And so what you see here are data points, experimental data points with their respective error bars. And so these two crosscuts are shown here, and you see that we see a quite nice agreement with the simulation. So this is coming from the reports we received from the reviewers, and I thought, you know, sometimes this is extremely useful, and I find that was actually very nice. So we did the whole design of the structure from the design of the polarizability, of the effective polarizability and the sign. But in fact, when you think in terms of Kerr condition, you obtain a very similar result. So basically, we found out that the positive case, so let me explain that. So this is the standing wave pattern without the membrane. This is the membrane located in the inflection point of this fringe. And this is the positive case. So this is, which one is that? So this is the second Kerr condition. So we reflect everything, meaning that I'm pushing on the system. So I'm deviating, I'm pushing the particle, toward the bright fringe. So this is the usual case. And here, this is the first Kerr condition. I'm forwarding most of the light in the forward direction. So I have a recoil. And so basically, the membrane is bending toward a minimum of intensity that is. So I thought that was actually a very nice suggestion to look at it in terms of Kerr condition. So now I would like to push a little bit more the analogy toward what I was telling you before, this analogy with cold atoms. And there are some experts in the room, actually. So blue detune trapping of cold atoms leads to a negative polarizability and to the possibility to basically play with a minimum intensity and locate atoms in this minima. So I would like to see that we can actually do that indeed and 3D trap a meta-atom, so this quite large mesoscopic particle, into a minimum of intensity, playing a similar trick. So just some very simple reminders. So here we're going to deal with a silicon particle of 200 nanometer, and so this is the electric and magnetic dipole. And so, of course, if the particle is bigger toward this radius here, you involve like some higher multipoles. So we're going to keep the same configuration, two counterpropagating beam at 1550. So what is the difference if I trap a silicon in vacuum? If I trap a silicon particle respect to a silica particle that does not support Mir resonances. So in the case of the silica, so this is the dashed lines, you have very flat response when you calculate the frequency, mechanical frequency of the trapped particle as a function of the radius. But things are very different when I involve silicon because I'm basically involving these Mir resonances, okay? And this is actually something similar in the trap depth that will also be much more, let's say, with a strong variation that comes from the resonances. But what is actually nicer, and this connects to the previous configuration, is that if I calculate the force along the standing wave pattern, so longitudinal force and radial force perpendicular as a function of the radius, and Z is basically the coordinate and the position of the particle, I'm going to see that I'm going to have, let's say, for a given position, I'm going to have, as I increase the radius for a fixed wavelength, some positive values for the force, negative. So I will not only influence the gradient, the magnitude of the force, but also its sign, okay? So I want to use that in order to trap in the dark. So this is what the simulation is showing, is that for fixed wavelengths, again, depending whether I have this radius or this radius, in that case, I will trap in a bright fringe. In that case, I will trap in a dark fringe. So this comes a little bit like in the middle of nothing. I'm just opening a parenthesis Another cool thing about trapping silicon particle, if you're interested in spinning them, there's a whole community trying to spin these things very fast in vacuum, is actually to have like super torque. And this is a collaboration with the group of Yuri Kivchar. And so in this simulation paper, so this is a similar experiment, but instead of having like linear polarization, we use two circularly polarized light of different helicity. And by playing on the anisotropy of the cylinder as well as the absorption, depending on the wavelength, so basically, Ivan has been able to really show that there was a possibility to reach torques that are really of very high values. Anyway, I close the parenthesis. So now I want to show how we do the trapping in the dark experimentally. Those of you that are familiar with colloidal chemistry, they know this is very difficult to grow this silicon particle, especially if you want a very low size dispersion. It's very complicated, and I asked my colleague once that is an expert in this field, and he said, never in my lab, this is too dangerous. So basically, there are just a couple of groups, I think mostly one group in Japan that is an expert in synthesizing this particle. So we went a little bit closer to what we know, and a top-down approach. So doing lithography basically on an homogeneous film of silicon, but using a sacrificial layer of silicon nitride in order to release them in solution afterwards, okay? So this is actually a very simple approach to obtain this silicon marshmallow, I call them, and with a quite high, actually, concentration. And then the advantage you have, of course, compared to colloidal chemistry is that, as far as I know, I'm not a chemist, but you can only grow them circular. With this technique, you can really play with the geometry, which is kind of an advantage if you want to engineer the mode. So then this is the experimental setup. So this is, oops, sorry for that. This is a standing wave pattern, again, at 1550. And so what we see here is a particle made of silicon that is trapped. Good news, wow, we managed that. But we don't know, of course, where it is. So now we need to find out whether this is trapped in a dark fringe or in a bright fringe, and whether by changing the parameters, we can basically demonstrate that we have a control over the sign of the force, or better said, where the particle is going to be trapped. So what we do in practice is that, again, we trap in vacuum and we measure the power spectrum density. That means we monitor the position as a function of time. We do a Fourier transform. We observe this Lorentzian curve. And this is along the z direction, so along the optical axis. For two different particles, we take basically the frequency, the mechanical frequency for these two cases, and we plot them as a function of the radius of the particle, okay? And so we do that also for silica in the experiment together with the simulation, and we show that basically, so silica is flat, like in the simulation, and you have more variation for silicon. If you put the model together and you use the power of COMSOL, you can identify that this a priori would correspond to dark, this to bright, and this to dark again. But again, this is an indirect proof, so we want to observe what is actually happening experimentally. So the way we do that, and there was a very clever idea from Bean, was to use the fact that, okay, strictly speaking, this is a multipolar response. There is superposition of different multiples. But eventually, electric and magnetic dipole are going to dominate. And so because they are perpendicular to each other and they scatter light in different directions, you can use that in order to observe what the particle is. So what COMSOLs tell you is that if you are on a bright fringe and the field is polarized, so perpendicular to the plane of the screen, you have no scattering in the perpendicular direction. So if I put a detector, I will not detect any signal. If I do dark trapping, I'm going to have actually the opposite situation. And so just now, imagine that experimentally, we're going to change the angle theta. So this is theta equals 0, and then we're going to rotate the orientation of the electric field. We're going to also rotate the orientation of the scattering lobes, and we will be able to check consistency. So basically, this is silica. This is this particle of this radius. They both show at 0, so this situation, no scattering. So this is the normal case. I'm trapping in the bright fringe. But for these two other sizes, I'm actually trapping in the dark. I change the rotation of the polarization, and basically I'm going to check that there is an opposition between these two situations, confirming that basically this is an evidence of trapping in the dark. How much time do I have? 5 minutes, including the questions? Yes, so I'm just going fast on why we're interested in using this trapping in the dark. In fact, for very similar motivation that the atom community is using them. Possibility, for instance, to couple these levitated nanoparticles that are mesoscopic objects, massive ones, to, for instance, surfaces, in particular, for instance, near-field cavities, like this is just an example of a near-field photonic crystal nanobeam. But of course, also to probe surface force field of different kind, check the decoherence basically introduced by the surface. So there are many things we need to learn, let's say with this levitated nanoparticle. I admit copying a little bit what people are doing with atoms, but this is truly what we do, and we're just using the toolbox in order to learn about the system. So I'm finishing here because I'm just going to use, let's say, the time of my conclusion, saying that you can also use metasurfaces to cool down levitated nanoparticle. So there's actually a metasurface here, some electrodes to apply a force and to apply a feedback, and we can nearly cool down the center of mass motion of this levitated nanoparticle to low phonon occupation number. We are not still in the quantum regime, but we are approaching very closely. Of course, what you want to do in that case is to play a little bit with complex phase front and use the whole capability of meta-optics in order to actually do things that are a bit more complicated, like, for instance, studying interactions between different nanoparticles, and etc. So I hope I've convinced you that, again, this community that knows a lot about engineering of meta-optical system can actually really contribute to this fascinating field. And I thank you for your attention.
Thank you very much. Okay. Thank you very much for the nice talk. So we have time for questions. So yes, please.
Yeah, thank you, Romain. Very, very nice. So I was wondering in the last part about two-photon absorption in silicon, and whether you see a difference when you trap in a bright or dark fringe, if you see that there's some indication that the temperature of the nanoparticle is different, for example, or something else?
That's a very good point. We didn't look at it. For sure, this is the limitation. So this is a proof of principle with silicon, because that was easy for us to do that. But the idea is to move to other materials to avoid this absorption, this two-photon absorption, because that would be an issue. That would be, so of course, your point is valid. So being in the dark, you are less exposed somehow to photons, and probably there is less absorption. This is what shows what is shown in the calculation. But still, this is not enough. So we will have to change material, for sure.
Okay, thank you. Anyone else? Okay. Yes.
So compared to atoms, the particles have a finite size compared to the wavelength.
Yeah.
So I wonder if you want to talk about actually the inevitable overlap. It's not really dark on the edges of the particles.
Yeah, that's a very good point. So this is not indeed, and so a significant portion of the volume of the particle going to be exposed to, of course, to the side bright fringes. And so this is a little bit connected to the questions we had before. So this is trying to identify the regime where we're going to really benefit from that. So there are two interesting things. Recoil will be decreased. Heating will be decreased, or these absorption processes. But the most important first, we need to solve these things, of course, is more the control of the distance to the surface. So you know, an experiment like with two colors, one that basically attract the particle, for instance, to the maximum of the near field at the interface, the other one that is blue detuned that push the particle, and by playing with the ratio between these two intensity to be able to very accurately control the distance. This would be very important for us for what is coming next.
Thank you very much. One more question? Yes?
Hello, Romain.
Hello.
Excellent talk. Thanks a lot.
Thank you.
So when you were showing the positive and negative forces and explaining them in terms of Kerker conditions,
Yeah.
I mean, I was thinking on the same lines until I realized that you're putting your meta surface on a standing wave. And so I don't know what's the meaning of the Kerker condition inside a standing wave if you're exciting them from both sides. And have you thought about it, or?
This is actually a very good point. So this is not strictly in the Kerker in the sense, you're fully right, about like sending a plane wave on the particle, true. But basically an equivalent where I would say the position of the particle will kind of break the symmetry depending on whether my polarizability is positive or negative. Okay. So at least this is the way I understand it. But you're fully right. Strictly speaking, this is not a true Kerker, because Kerker would be with one illumination.
Thank you.
Yeah, you're right.
Thank you very much. So let's thank our speaker for the very interesting talk. We call the next speaker. Yes, there's a mic here. So, okay, let me do the introduction. Hello. Thank you. The next speaker is title of his talk is "Dielectric mean nanostructures and metasurfaces from quantum emitters" from Aurelio Cuichet. Let's thank our speaker. Thank you.
Thank you, Mr. Chairman, for the introduction. So first, before starting, I would like to thank the organizer for the kind invitation. So it's a great pleasure to be here today. So with my colleagues of the nano-optics group at CMS, basically one of our axes of research that we develop is enhancing and control the emission of quantum emitters. And this you will see with dielectric nanostructures. So if we start with this really generic equation for the emission of a quantum emitter, basically there are three terms which are related to the excitation, so basically the pumping rate, to the emission with the local density of states, and to the let's say to the collection efficiency, including the directivity of the emitter. So basically we try to address these three parameters, these three terms of the equation. And this is particularly interesting and important because it has direct application for long range and I would say also on-chip quantum communication. So usually the quantum emitters that are considered in this work are semiconductor quantum dots, or eventually potentially also colloidal quantum dots, defects in crystal like color centers in nanodiamonds, or 2D materials and defects in 2D materials, and also nonlinear sources. So it's a non-exhaustive list. And these emitters, they are embedded in actually in really complex and beautiful architectures. So in integrated photonics, you see that there are already really complex systems where these quantum emitters are integrated in quite large structure, then coupled to optical fibers. So here you have a photonic crystal, for instance, or even, I took this picture from Candela, the French company. This is the art of a quantum computer where you have this kind of epitaxially grown quantum dot, let's say, in this multi-layer resonator. But what I want to emphasize here is the size of this structure, which are, let's say, micronic. I mean, this is 1 micron here, 10 microns, so I would say it's quite big. So the strategy that we develop at CMS with my colleague is more based on nano antennas. So here I would like to say that actually these nano antennas can also be integrated in these micrometric structures. And so these nano antennas, they are much more compact. Here we are dealing with structures which are about few hundreds of nanometers. And of course, really compact, but the price to pay for that is usually they have a really low, rather low quality factor that can be a bit compensated by the mode volume, which is really small. So at the end of the day, we still get a Purcell enhancement, a Purcell factor on this system. So there are a lot of works that have been developed in nano antennas, in particular in plasmonics. But here, the system that I want to present today, and that has been introduced by Romain Quidant just before, are these high-index dielectric nanostructures. So it's quite a hot topic now for, let's say, 10 years, I would say. And why they are particularly interesting? Because you can have enhancement and confinement of the electric field, but also of the magnetic field at optical frequencies, and this with lower losses compared to plasmonic systems. So these appealing properties, they emerge because of these mere resonances with this simple resonance condition that links the size of the structure with the wavelengths in the material. So this is why here you want to go to high index, because basically you will shrink the light in the system. And if you fix this integer, which is the order of the resonance, you see that by simply changing the size of the structure, basically you can tune the wavelengths of the resonance. And so you can deal with single structures where you have simple resonances like electric and magnetic dipole, the first resonance of the multiple decomposition. And of course, you can also couple this structure, and they are the building blocks for, let's say, metasurfaces. But here I would like to show you that even with single nanostructures, we can already obtain really interesting optical properties. So here in this work, which is already quite old, I would say, we have performed a forward-backward experiment on single dielectric nanowires. So they are made of silicon. So here the idea was to measure the dark field spectrum in transmission, so it's forward scattering, and the dark field spectrum in reflection for the backward scattering. And for that, we used epitaxially grown silicon nanowires with these two polarizations for the light, TATM, but also lithographied silicon nanowires in collaboration with our colleague in Grenoble and in Toulouse. And I just show you here, I flash one result for a specific size, so a diameter of 100 nanometer. So you see here, for a given polarization, T, you have the forward spectrum and the backward spectrum, and you can see that they are already quite different. And if you turn the polarization, they are again more different. And if we focus specifically at these three wavelengths here, the three dashed line, this is the simulated angular scattering of the light. And you see that at this wavelength, for a TE polarization, you have full backward scattering. And if you turn the polarization, you will have full forward scattering. Then you just look at the different wavelengths. And here you have only full forward scattering for both polarization. And then at this wavelength, you have either no scattering or isotropic scattering. So you see that with a single size of the structure and just two polarization, you have already completely different behavior for the scattering. Well, so I'm not going into detail here. We have performed systematic study, and here you have this forward-backward ratio. So when it's red, it's full forward. When it's blue, it's full backward scattering. Here you have the size, the section of the wires, and here the wavelengths for only one polarization. And you see that depending on when you are on these maps, you can have full forward or full backward scattering, or also isotropic scattering. So just to show you that here, we have this kind, so it's funny because Romain mentioned it just before, but this kind of Kerr conditions. So here, of course, we don't have mu equal to epsilon because mu is equal to 1, but because of interferences between electric and magnetic resonances, we have this quasi, let's say, or these pseudo Kerr conditions. Well, so I go back to this, to the, let's say, the control of the emission of quantum emitters. So I go back to this equation. And in the recent year, we have addressed several terms of the equation, in particular with TMD monolayers deposited of, let's say, complex antennas, where we try to observe the effect of the near field in the generation of excitons in this monolayer system. Also playing on this term on the local density of state for electric and magnetic dipolar transition in rare earth ion deposited on structures. So if you're interested, you can have a look at these papers. But here, I would like to focus on punctual emitters, so single photon emitters that have to be deposited in the vicinity of nano antennas. And I want to show you that even with really simple geometries, you can already enhance and direct the emission of these single photon emitters. So, as single photon emitters, we use impurities in diamond particles. So I think you already know these color centers. Basically, they are made of impurities close to vacancies, and these form a complex which is well isolated in the gap of diamond. So by changing the impurity, basically, you can change the emission line, and this can approximate it at two-level system, so a single photon emitter. So in our work, we mainly work with nitrogen vacancy centers, in particular the negatively charged NV minus here, with a zero photon line at 637 nanometer, and also with the silicon vacancy center, which emits around 735 nanometers. So these particles, these nanoparticles with this center, they are obtained in collaboration with Vyacheslav Agavonov in France. So here I will mainly focus on these NV centers. Yeah, of course. And the structure, so they are made of industrial grade silicon on insulator wafers. So we start with this perfectly 90 nanometer single crystal layer, and then of course we do high resolution lithography, so we can obtain basically all the geometries that we need for experiments. Well, so we started with really simple system, dimers, as you can see here, and we focused on 3 different geometries, let's say small ones, intermediate ones, and big ones, and different gaps. And these geometries are either non-resonant, so here you have the scattering spectrum from the non-resonant structure in the emission band of the NV center, here, so non-resonant. The intermediate size is resonant, and let's say the big structure is also resonant. And the idea here is to deposit the emitters at the center of the dimers, because this is where we expect pulsar enhancement, so something around 2. So for that, we adapted the techniques, which is called AFM nanoxerography. And the idea here is to deposit a monolayer of PMMA, which plays the role of an electrode here to retain the charges. And then we bring the tip, so we have AFM resolution, okay, and we inject charges in this electrode. And we put our solution of nanoparticles, which are negatively charged, and because of Brownian motion and electrostatic interaction, they are trapped at the dot here. So what we can do basically is position single nanoparticles down to the single photon regime, but also, and this is also important, we can statistically control the number of particles that we deposit. So if we need more particles for specific application, we can also do that statistically. So we applied this method to our dimmer sample. So each dot here is a dimmer particle. And you can see the photoluminescence map after deposition. So here we have a really bad contrast, sorry for that, but we have a spot on each structure, even on the non-resonant structure. And you see that we have a nice spot. So we have a large scale resolution. We can do matrices of emitters deposited on structures. And if we perform, so this has been done with AFM nanoxerography. And if we do a characterization of these dots, we have nice deposition of, again, of this statistically controlled number of emitters with the NV center signature. And in the majority of the cases, we have either a single photon or 2 photon emitters. So why? Because we cannot control exactly the number of NV centers that we have in our particles, but still we have a really nice control. So we have, let's say, large scale deposition and also a great accuracy in the gap of the structures. I will say accuracy around 50 nanometer. So I'm going a bit fast here. We performed a systematic study of the sample. We performed lifetime measurement in order to check the Purcell effect in these structures. And what we observed, basically, it was an enhancement of the photoluminescence of 1 order of magnitude, which does not match the Purcell enhancement of about 2 that we measured, and which correspond to the simulation. And basically, this is due to an antenna effect. Actually, the dimmers really act as an antenna and redirect the light in the numerical aperture of our microscope. Okay, so if we go a deep further in the analysis of the coupling, so if we take our antenna, we send a plane wave, and we compute the scattering cross-section, or here it's the extinction cross-section of our system. This is the response, where we have the electric mid-dipole, and here the magnetic mid-dipole also. And then what we do here, we put a dipole, and as a function of the wavelength and as a function of the orientation of this dipole, we compute the average of the intensity of the electric field, okay? So it tells you in the band of the NV center which dipole, which orientation couples, field energy couples to the resonance in the silicium here. And you see that for this intermediate size that was resonant, it's mainly the X dipole that coupled to the system. So we couple to the electric dipole, so the X dipole coupled to this resonance here. But if you slightly increase the size in just one dimension here of the dimer, you see that the same simulation is completely different, and now it's the Y dipole that coupled to the resonance here, and basically it creates a vortex of electric field, so it basically corresponds to the magnetic resonance here. So experimentally, we do not control the orientation of the NV centers in our nanodiamonds, but I will say that the structure actually operates a kind of vectorial selection on the emitters. Only NV centers that have a projection along the x-axis will couple to the resonance, and here similar for this structure, but for the magnetic dipolar resonance. So we can go to a different system, a more complex system. For instance, as a proof of principle, we try to control the directivity of the emission of these emitters. So we try to address this term of the equation. And here we use an optimization algorithm. The idea was to send most of the light in a window here at the emission wavelengths of the NV centers, and the fitness parameter is this ratio. Basically, it's the integrated intensity in that window divided by the rest of the intensity in the half space here. So for that, we used, I would say, two strategies, one based on resonant nanorods, so 5 nanorods that are allowed to move in a 1 micrometer square area here. And if you remember the beginning of my talk, we know that the interferences in this kind of rectangular system can give, let's say, angular scattering. And the second strategy was to use 10 nanocubes, so same amount of matter, same amount of silicon, but here the algorithm has more degrees of freedom to move the cube to get the best directivity. So I'm going a bit faster. So we run our algorithm that at some point converge to different geometries. So here, for instance, I show you I flash 2 results. So we have an X dipole. You see the emission in the far field. And once it's coupled to a structure or another structure optimized for X dipole, you see that we expect a really nice directivity. Interestingly, both strategies based on resonance system and non-resonant nanocube gave more or less the same directivities. And we fabricated our systems. So each dot here is a structure. They're scattering in the red because they correspond to the resonant building blocks with the magnetic dipole here and the electric dipole. In green or blue here because they are non-resonant. So here you see that we have absolutely no resonance. And this is what we expect in terms of directivity in this real multi-layer silicon on insulator wafer. So this is our reference, and this is for scalar emitter, so average over 3 direction of space. And this is what we expect. So for X, Y dipole, and average emitter, we position our nanodiamonds with really high accuracy. So this is the job of Swao Palais. He has done a really great job here. And so we checked that we had NV center emission, again, on almost all the structure, with an average 2 or 3 NV centers per nanoparticle. And I show you here the typical results of what we obtain, a really nice directivity of the diamonds coupled to the structure. And here we cannot control the emission, the dipole orientation, but they are robust. If you couple a scalar emitter to this kind of antenna, you expect directivity, and this is what we observed. So I'm going to switch this, and it brings me to the conclusion. So we developed positioning techniques where we can control statistically the number of emitters down to a single nanoparticle, and then we can position these emitters on our simple nanostructure to observe pulsar enhancement because of coupling to mirror resonances, and we can design much complex antennas to get directivity, and we are going now to more complex systems, 2-dimensional systems, to enhance the emission of these quantum emitters. I would like to thank all my colleagues, in particular from the nano-optics group, and I would like to thank you for your attention. Thank you.
Thank you very much. Okay, for the sake of time,